So today I'd like to talk about accuracy in DFT calculations. Let me first of all acknowledge the contributions that were essential to some of what I'm going to describe. William Dawson, a very talented student who's now at Riken in Japan. Michael Account, who's now at PNNL, and Martin Schlipf, who's now working for the VASP company. And the people who fund this are the Midwest Center for Computational Materials, based at Oregon National Lab. So that's a DOE-funded center, and the places that provide large computers to do what we do are both Oregon National Lab and NERSC in Berkeley. All right, so I'll try, if time permits, to go through all these steps. First, I'd like to give some context of what we do and what we are trying to achieve and how that leads us to considering the accuracy of approximations. We're interested in DFT molecular dynamics simulations. That leads us to the problem of comparing exchange correlation functionals. That will lead me to the question of pseudopotentials. How good are they, and how do we check that they are accurate? And what are the means to generate reference data to be able to do this kind of assessment? And last, if time permits, I will briefly make a few comments on a technique we developed to accelerate hybrid DFT simulations in a way that keeps control on accuracy. So the context is that of DFT molecular dynamics simulations. So what we would like to achieve is be able to simulate large complex systems. Give you an example here on the left of such a system. This is a silicon surface which is terminated by hydrogen atoms, and it's in contact with water. And so the goal would be to simulate this from first principles. And since it's a large complex system, you need to simulate it for a long time. So it's usually not possible to simulate large systems of thousands of atoms and learn much about them, because time dependence and thermodynamics actually matters. So the tool we're going to be using is first principles molecular dynamics based on density functional theory, because that's what's feasible. And the critical thing is that the choice of the density functional theory or the exchange correlation level does affect the structure of these systems. In particular, one story that has been ongoing for decades is whether water is liquid in normal conditions if you choose different types of exchange correlation functionals. We're also interested in understanding the electronic structure, in particular excited states. What is the band alignment across an interface like this one? That usually requires going beyond DFT, like GW calculations, and also spectroscopy of such a system, so both vibrational spectroscopy, IR and Raman, but also optical absorption, and that would be based on calculations using the beta salpeter equations like the ones that Chao was mentioning yesterday. So this is kind of the general setting of what we're trying to achieve. Now, to compare density functional theories and approximations, there's been this concept of the Jacob's ladder that's been proposed. And presumably, in that picture, you would start from the simplest density functionals and make them gradually more complicated, like generalized gradient approximation, meta GGA. I've put examples of such functionals here, hybrid DFT, such as B3-LIP and many others, double hybrids. And then the idea would be that as you keep improving those, you're climbing this ladder, and everything gets better and better until you reach whatever version of heaven you have, right? So that would be very nice if that was the case, because there would be a systematic way of improving things. Now, I'm not so fond of this picture here. I'm actually fond of Escher, and that's probably a more accurate picture of what's going on. You don't have a one-dimensional space of functionals where you can improve systematically in one direction. When you improve for one property, it might degrade another property, right? So what we have is a collection of functionals, and we have to assess them, but for different properties. We cannot just claim that if they get better for one property, they will be better for everything else, right? The practice shows that's not the case. This picture is not mine. It was taken from a paper by Lorena Vega. So back to the kind of simulations we want to do. So first principles molecular dynamics is something that I expect many of you are familiar with. Just to summarize it here in one slide, this would be the following scheme where we consider ions to be classical particles. So the nuclei are classical. And we're going to just use Newton's equation of motion to move the nuclei, and then density functional theory to compute the forces that act on the nuclei, and repeat that again and again at each time step of our simulation to simulate our system. So this was really pioneered by Carl Parinello back in '85, and many refinements came later on, and many ways to accelerate that process led to a lot of understanding of rather complicated systems. So what you have on the right, in this box on the right, is the solution of the Kohn-Sham equation. So something that I expect most of you are completely familiar with. Just again, to sort of summarize it here, we're going to be solving the Kohn-Sham equations for each of the orbitals phi I, and using a potential that depends on the charge density. It consists here on a potential due to the nuclei, and that's in general, it should be the Coulomb potential, a Hartree term, and an exchange correlation term that depends on the density, and possibly also on gradients of the density or even other things. Density itself is the sum of squares of the orbitals, and we have to enforce orthogonality of these orbitals. So this problem, if you just state it like this with Coulomb potential, is very difficult to solve. It sort of reminds us that electronic structure, even if you have a single atom, is a multi-scale problem. You have things happening at all scales between order 1 and order 1 over z. So as soon as you start looking at something that's not hydrogen, it gets complicated and numerically difficult. So there are well-developed all-electron methods for that, and I list a few here. The linearized muffin-tin orbital method, linearized augmented plane wave method, full potential linearized augmented plane wave method, same method with additional local orbitals. So they get increasingly complex. Gaussian basis sets that are popular in chemistry, Slater-type orbitals, or just numerical bases. So a lot of these things have been developed, and they deal with all electrons. What I represent here on the right is the picture of the first methods I mentioned, so-called muffin-tin orbitals and AEPW methods. They usually partition space in spheres that are called muffin-tin spheres, in reference to the muffin-tin object you use to bake muffins. And the solutions are found in different ways inside and outside these domains. And a matching of the solution has to be done on the boundary of these spheres, right? So that's the way they are able to deal with all electrons. So what I want to say is here that to reach convergence and to be confident in the accuracy of a result that you obtain with this method is definitely possible, but you need to really understand these methods really well. And you need expertise, deep knowledge of what's going on in these calculations, particularly when you start adding local orbitals to these spheres, because you realize that your basis was not complete enough. You have to know where to put them, which kind of orbitals you should put. It's a rather tricky business. On the other hand, you have the other approach, which consists in removing core electrons altogether, using pseudopotentials, which are then smooth potentials. And then if they are smooth, you can use a plane wave basis. So if you use a plane wave basis, it's simple to converge. You have just a single parameter, which is your plane wave energy cutoff, and you can just push it until everything converges. Nice. But now you must control the approximation you made by removing these core electrons and substituting them with a pseudopotential. And that's where the problem lies now. Now, the idea of a pseudopotential, I should point out, has been found to go back all the way to Fermi. It was in a nuclear context, but it really became more of a tool for electronic structure with the work of Jim Phillips and Kleinman. So I will just show a few cartoons here to sort of illustrate what a pseudopotential approach is. And in the case of silicon here, I show here what happens if you just use an all-electron problem. So you have the potential being the Coulomb potential. And you find that the wave functions here are going to oscillate a lot in the region of the core and then decay smoothly outside. And then you will arbitrarily somewhat declare that there's a valence region, which is where chemical bonding will take place here. So for instance, in the case of silicon, there will be the 3s and the 3p orbitals. And the other orbitals, like the 2p and 2s and 1s, are going to be confined inside the core. And you're going to use that to separate your problem into core and valence. So if I just zoom now on the core region, this is still all electron. I see the 1s orbital multiplied by r here, and the 2s. Of course, the question is, there's still overlap between 2s and 3s, and where do we cut? And that's where all the art of making a pseudopotential comes. So if you do make such a pseudopotential, you get the following picture. You have to choose somewhere a point where you will ensure that a pseudo wave function will match the exact one. And then inside of that radius, you will continue that wave function smoothly so that it's nodeless and just goes to 0 here. And having done that, you just completely remove the core electrons. You have a problem with just a nodeless function, which will now be your ground state. And the potential, on the other hand, will now be different from Coulomb. It will have a smooth shape here, and it will reach 0 at a finite value. You notice here there are 3 different potentials, because now for different angular momenta, you will have different potentials. So that's a non-local potential. So that's just a cartoon. So if you want to put that in a little bit more precise definition, this is what a pseudopotential is. If this is your all-electron Schrodinger equation with the minus z over r here, the pseudopotential would be something in which you have a pseudo function here, pseudopotential for each L, each angular momentum, and a pseudo wave function here that satisfies this same equation with a different potential, with the condition here that the pseudo wave function has to agree with the exact wave function beyond a certain radius. You're going to choose that radius. Now, this is actually a little bit too restrictive in some sense. You can actually make this potential here be a completely non-local operator, not only having a local potential, but also some projectors that you are free to choose to try to match the all-electron wave function. And we will come back to seeing what these look like. So let me just say, show one example of a recipe to make a pseudopotential. I'd say it's a recipe. It's not the recipe. There are many different ones. And I don't have the time to go into all of them. But this would be one way you could do that. You would first, of course, solve the problem for all electrons. And then you could try to generate a pseudo wave function, the UPS of R, that has to be nodeless, will match your solution beyond RC, and is smooth within RC. And once you have that, you can invert the Schrodinger equation, right? You know that if it satisfies the Schrodinger equation, then you can reconstruct the potential here by just inverting the Schrodinger equation. Now you see the denominator, it contains the function itself, so you have to have a nodeless function. You cannot bring this radius, this cutoff radius, inside of the outermost node of the all-electron function. So that's a constraint you have. That's just one possible way of doing this. So if I want to try to make general comments about the problem of generating pseudopotentials, the first thing I could say is you could state that as an inverse problem, right? We know what the all-electron problem is, and we try to reconstruct a pseudopotential that will mostly reproduce the correct answer. Now, I don't know if that can be done in full generality of having any possible function in some function space that will be a pseudopotential, but in practice, you have to reduce that space to one that has only a few parameters that control the pseudopotential. So those are obviously the nuclear charge, the choice of exchange correlation functional, because you do that for a specific exchange correlation functional, because you have to solve the Kohn-Sham equations that affects your all-electron solution and therefore your pseudopotential. So you have to make that choice. You have to choose this cutoff radii, and there are constraints on that, like I mentioned before. You also have to choose up to what angular momentum you're going to be describing things correctly. ideally infinity, but in practice you have to limit yourself. And then the occupation here is what's the charge of the atom that you're representing. Neutral is one choice, but it's not the only choice, right? So these are the parameters that we have to try to generate pseudopotential. Now, as you keep in mind that it's not possible to generate a potential for any choice of these numbers. Sometimes the procedure just doesn't converge. It doesn't generate a potential. And the other thing that we have to keep in mind is the generation of the pseudopotential is a highly nonlinear problem. And you would think, well, if I want to try to optimize it, I could try to compute my derivatives with respect to these parameters, but in practice, it's really not usable. You can't really rely numerically on derivatives with respect to these numbers. Now, even if you can generate pseudopotential, the question then comes of how transferable they are to other situations. Right? You know it's okay for the atom because that's the thing you use to derive it. Now, how good it's going to be when you use it for something else. So the question is how accurate it is in another environment, not just a single atom. Now, one problem, for instance, is that we have to choose this atomic charge. And sometimes that's not what happens in the actual environment of the atom. So take the example of oxygen. If you generate your pseudopotential for a neutral oxygen, that's good for the atom, that's neutral. But when you put that into a crystal or an oxide, well, very often oxygen is going to grab 2 electrons and become charge 2 minus. Now, how good is the pseudopotential in that situation is a big question. So on the theme of transferability, the question you have to ask yourself is how good is a pseudopotential when the atoms get close? So remember that we said that the solution of the Schrödinger equation with the pseudopotential is going to be correct outside of this cutoff radius. And that means that inside the cutoff radius, it's non-physical, right? Now, if you look at the spheres defined by these cutoff radii, they're not that small. You cannot make them arbitrarily small. Like we said, if you get inside the outermost node of the wave function, you can't do it. So if atoms get close to each other, you can reach situations where the region where the solution is physical disappears. And if you look at things like the oxygen dimer, the nitrogen dimer, you will see that this region where supposedly you have an accurate solution is pretty small. Now, how bad is that? Is that a problem? How do we check that? Last issue of transferability is one I want to mention is the transferability to other exchange correlation functionals. By that I mean using a pseudopotential that was derived using one exchange correlation functional in a calculation that uses another exchange correlation functional. Now, why would you do that? It's done very often. Well, for one reason, first is that generating pseudopotentials is quite an involved process, and not everybody generates pseudopotentials for all existing exchange correlation functionals. Just to give you an example, there's a well-known library that implements exchange correlation functionals called libxc. That's used in many electronic structure codes. And there's something like 800 functionals in it. Well, there's no way we're going to generate potentials for all of these. But the other thing is, some of these exchange correlation choices do not make it easy or make it impossible to actually invert the Schrödinger equation. Right? And one example is matter GGA, where the potential depends on gradients of the orbitals, and hybrid-DFT also, which is problematic. So one question we have is then, for instance, what would be the error that I make if I use a pseudopotential that was generated with a PBE functional, but then I use a scan functional instead? How bad is that? I call that, or like a better word, cross-XC error, using two different.
Ask a question.
Yes.
Can you say a little bit more why it is difficult or even unfeasible to generate pseudopotential for HSE?
Well, you have, for hybrid, it's not impossible. In fact, it's possible even for matter GGA. It's just that it makes the inversion problem impossible. So you can still generate by trial and error.
You can always fit.
What's that?
You can always view this as some sort of least squares problem. Fit.
Right. And it gets pretty tricky also because you would like the pseudopotential, and particularly these projectors that I was talking about, to be short-ranged. Now, when you have a hybrid functional, you cannot simply decide that those are short-ranged. You might have long tails, and that makes the whole process more difficult. It's not impossible, and some people have claimed to make pseudopotentials for hybrids, but it's not an easy business at all.
But it's still possible, and there's some value.
There is?
There is some value in it, if that can be done.
Some validity.
There is some value. So if I understand correctly, that it is difficult, but it's not completely impossible. One. Two is that if somebody can do it, can be appreciated.
That's right. I'm not sure it would be
appreciated.
So advisable, but that's a longer discussion.
I see.
Yeah. And finally, there's another type of transferability that you want to worry about, is that when you generate a pseudopotential for an all-electron atom, you're basically reproducing what happens at the energies of the bound states. Now, when you go to another environment, like a solid, there will be some of your wave functions that would correspond to a different energy. They're not the energies of the bound states. So one question is, how good is your pseudopotential when you start to go away from these bound state energies? And can you say something about that? Now, at least on this last one, there has been progress, and that's the concept of norm-conserving pseudopotentials. And that's something that's been introduced by, actually originally Shaw and Harrison quite long ago, but really made more known and popular by Hamann, Schlüter, and Chang. And that basically is based on the observation that if a function u satisfies the Schrödinger equation for an energy E, and here, let's look at this E as a parameter. So I'm not thinking only of u being an eigenstate here for an eigenvalue, but I'm saying if I try to solve this for any E, and E approaches an eigenvalue, it's been observed that this equality holds, which says that the log derivative of the solution, which is really what we worry about, the ratio of the derivative of the solution to the solution, if you derive that with respect to this E value, this is going to be equal to that quantity here. Right? So since this is true in the all-electron case, the point would be that if we make sure that it's also true in the pseudopotential case, we will have the same log derivatives here near this energy. It means that as we move away from a bound state energy, we will change the solution in the same way that the all-electron problem does. And that's an extra level of transferability. So that was the concept behind norm conservation, and the idea being that if you ensure norm conservation of your pseudopotential, then you have good transferability properties. And to do that, you just have to ensure that when you integrate the charge within a given radius, you get the correct value compared to the all-electron charge. So this was a first step into making pseudopotentials more transferable. And there is a later elaboration and refinement of that, which was developed by Don Hamann, and which is called optimized norm-conserving Vanderbilt potentials. This is a complicated recipe. I mean, it takes care of many things, and we don't really have the time to go into the whole detail. Let's just look at it as maybe a black box here that would take these input parameters that I described before and gives you a potential operator here, which has this form here with these projectors, keeping in mind that that doesn't work for all choices of parameters. This is an example for silicon here. The local potential that would be given here, that's the same that acts on all angular momenta, is this shape here. And those are the projector functions that come in addition. Now, I cannot overemphasize the importance of the work of Don Hamann in all this. He's the one who really made the whole thing practical. And he's the one who made it possible to have entire periodic tables of pseudopotentials that actually do the work. He's a real pioneer in this. And not only he explained to us how to make it, he provided the software to make it and distributed it to everybody. So this is an amazing contribution. I want to really emphasize that. All right, so suppose that we generate a potential by choosing these parameters here and making a pseudopotential. How do we validate it? So the normal procedure would be make a pseudopotential and then try to go and compare your results in another setting, like a solid or a molecule, and compare it to all-electron data, right? So you could do that on an atom for excited states, because those are not something you used in a derivation of your potential. You could compute polarizability, for instance, and see if it works well. In solids, typically you could choose to compare the energy versus volume curve that you get with the pseudopotential and compare that to an all-electron calculation. Typically, you could use one of those very elaborate FLEPW plus local orbital calculations. Now, can you optimize this process? If you find that you generated a pseudopotential and you're not so happy with the way that it reproduces this. So if you want to do that, you have to define a cost function. And if you define a cost function, one thing you have to keep in mind also is you have to include in that cost function the cutoff of the plane wave method that you're going to need to do the calculation. Why is that? Well, if you neglect that, you can make pseudopotentials that are extremely wild and hard, and they will work very well, but they will need such a high plane wave cutoff that's not really usable. So that's a restriction. So you can try to define such a cost function and then try to see if you can optimize that. So that's one thing we've done already a few years ago. We generate a collection of pseudopotentials we called SG15. So that's basically the optimization loop that I was referring to before. And we generated a table that goes up to bismuth. So the cost function that we use includes, of course, the fact that we have to match all electron atomic wave functions, but also how big of an energy cutoff we need in the plane wave calculation to obtain that match. Then we use a training set that includes all electron calculations. Those were obtained with the FLEPW code called FLIR. And we included all the body-centered cubic, face-centered cubic, and also some binary Roxhole structure for all the elements that we considered. And we imposed that we had to reproduce these energy versus volume curves. And then we validated that on molecules, ternary compounds, perovskites, more sort of exotic compounds, ternary compounds, over 600 of them. Now, as I mentioned before, you don't have derivatives of your parameters available with respect to your parameters. So this was kind of a search, sort of derivative-free optimization. And we use a simplex method to do that. So we sort of went through this repeatedly and tried to narrow down a simplex that would find these parameters until we match, we can minimize this cost function. And we distribute those on our website here. They're available also for quantum espresso format that can be used. Here I want to emphasize the work of Martin Schlipf, who was the first author on this paper, was a remarkably talented postdoc. He was very persistent and made it to generate all these potentials. And that's a lot of work. And it goes back to, do you want to do that for every exchange correlation functional? Maybe not. That's a lot of human time. It's not yet completely automatic. Well, even after having done that, we still have a few remaining questions, right? So, for instance, what is the validity of forces and stress tensors if you use these pseudopotentials? Those are not things that we put in the recipe in the optimization loop. Now, those are not easy to compute with these all-electron methods. The stress tensor, for instance, is not directly computed. It's usually done by fitting an energy versus volume curve and then trying to take derivatives of the fit. There's a problem of also what happens when these muffin-tin spheres that are used in these methods start overlapping. The method technically doesn't remain valid in that case. What about excited state energies? Are these pseudopotentials going to be able to describe properly band gaps, for instance? And by properly here, let's make sure we remember, we're not talking about comparing to experiment here. We're talking about the comparison of the pseudopotential calculation compared to the all-electron calculation for a given exchange correlation functional. So as bad as this exchange correlation functional is, that's what we're trying to compare, right? Well, there's this other cross-XC error that we mentioned before. So this altogether would mean that we need to include more properties in this optimization loop, excited states maybe. But for that, we would need something that's more flexible and easier to use than these all-electron methods. And we need something that's simple and easy to converge. So then the question is, how about plane waves? Right. So that's the thing that we were always told never to do. Don't solve an all-electron problem with plane waves. It's never going to work, right? Well, what I want to convince you of is that it actually works. And I will show you how you do that. So of course, you have a singular potential, so you need to regularize your pseudopotential, your potential. And you have to choose carefully what function you can be using to replace the Coulomb potential. So what we propose here is to choose a potential that will, by construction, reproduce the 1s eigenvalue of the all-electron problem. That's a very down eigenvalue of the 1s electron in our atom. But also, and that's a very important feature of this potential, it's norm-conserving within that radius. If you just take a naive regularization of Coulomb potential, like R function over R, the whole thing doesn't work. It will never converge. But if you pay attention to make it norm-conserving, suddenly you see that it works. Why is that? Well, if it's norm-conserving, you will have the correct solution outside of that radius. And that will help having correct solutions for the higher levels. So the way we go about that is we define first an analytic function for the wave function. We start from the wave function to replace the 1s wave function, which we know analytically, with a pseudo wave function, which is smooth, doesn't have the cusp at the origin. So we take this form here, an exponential of some function h of r. We know how the function should behave at large distance. It should just go to minus z times r. And we want the function to be smooth and have a finite limit at 0. Having done that, we can just invert the Schrödinger equation. So that's our Schrödinger equation. This is our eigenvalue. We know it. That's the one we want to reproduce exactly. Yes?
The previous slide?
Yes?
Why? For the limit at r, why do you assume that the remaining term is equal to r squared instead of r?
Right. I want it to be r squared because I want it to be flat at the origin. I don't want a cusp in the potential because that would, again, cause problem when I use Fourier transforms. Right. So I know my eigenvalue. I have defined an analytic function for my wave function. I insist on analytic because that's really will be critical to have a Fourier series that converges fast enough. Not some kind of cut and paste function that I make by fitting something at a finite radius and fitting derivatives. This would not work. You want an analytic function. So the potential is just simply given by this inverted Schrödinger equation. And now if you plug in the expression that I showed you before for the wave function, you see that it just depends on its function h of r and its derivatives, right? Simply expressed like that. Now remains the choice of that function. And we choose this expression here. So it's infinitely differentiable. And it's made of Gaussians and r squared times Gaussian and r times error function. All very nice functions. You look at the Fourier transform of this, it's very nice. Converges very fast. Now, we impose the norm conservation condition by adjusting this b parameter here. So b is not a free parameter. On the other hand, we have this a here that basically determines the range in which our potential is different from Coulomb. Right? So we have a family of regularized norm-conserving Coulomb potential that's analytic, parameterized by the number a. And if you take this number and push it to infinity, you recover the Coulomb potential. So what does it look like? This is for carbon. This is the potential for different values of this parameter a. It sort of gradually becomes deeper and deeper and deeper and approaches Coulomb potential more and more. The wave function here has the norm conservation property because it's exactly the all-electron one, but then it differs in a smaller and smaller and smaller volume. Right? And it's all infinitely differentiable, both for the wave function and for the potential. All right, so what we propose here is the unthinkable. We're going to use plane waves to do an all-electron problem. We use a Qbox code. That's the software we develop. Available. It's free. Let's first start with hydrogen. At least we should be able to do that. And we use the LDA in the Vosko-Wilken-Nuzer formulation. Now it becomes critical to choose which parameterization of LDA not necessarily the one of Purdy and Zunger, that's different, but this one, and I'll tell you why. And choose this parameter, and now try to solve the problem, increasing this parameter A until everything converges. And each time you change this value of A, you can increase your cutoff until you completely converge your calculation. So you can completely converge this calculation for any choice of A. Now, that means that the cutoff we need is going to be 6,000 Rydbergs. And that's the value you get for the energy. Now, the reason we chose this VWN functional is that there is this data here available on the NIST website, which is a database of LDA energies and eigenvalues that was computed a long time ago by Svetlana Kotochigova and the group of Zach Levine, Eric Shirley, and al. And that's available there. They claim to have solved this problem with an accuracy of 10 to the minus 6 Hartree. And they use a radial mesh that is logarithmic mesh, and they checked all the conversions of their approach to claim that accuracy. Now, we reproduce that within 1 to 10 to the minus 6. And we have a completely different method. It had nothing to do with a logarithmic mesh or anything. And we use that as a verification that we are actually indeed solving this all-electron problem. Of course, at a much higher cost, but we can get the same solution. All right, well, yes?
You change 8 from 12 to 13. The modification is within 10 to the minus 6.
That's correct. So we start at 12. We start actually below. I mean, you get pretty close to that, to these significant digits with even 8. And we push it, converge it again, push it, converge it again, and in the end, doesn't move on that scale. All right, so what happens for a little bit more interesting system than hydrogen? Well, just a diamond crystal here, nothing complicated. In this case, if you want to push this convergence, changing its parameter A and increasing your cutoff until things don't move, you get to 40,000 Rydbergs. That works. It's not for the faint of heart, right? I mean, you need a large machine, right? That's going to use a lot of memory. You need a code that scales, and that's where we spent some effort making a code that can use 100,000 cores and still does something useful. So this is not the kind of calculation we're going to be doing with molecular dynamics. This is a calculation we do once to validate things, right? It's a completely different use. So we can compute things like the energy, of course, but also the stress tensor and the band structure, in particular the band gap. What we observe is that there is exponential convergence when we increase the cutoff for a given A. And that's something we kind of expect because we had this potential that was basically made of analytic functions, right, and Gaussians. We also observe exponential convergence when we change A for converged calculation, which is a little bit less obvious. And one of the things I'd like to get here is to have some mathematicians look at these things a little bit more carefully and tell us maybe why and how, and maybe it can be improved or what. Anyway, so those are the numbers we get. So this is what we call all-electron plane waves, and we get a band gap of 4.14. If we now test our pseudopotential that we had made, well, we're pretty close, but not exactly on top. Look at data that you find online. The VASP result that's posted at Materials Project is pretty close too. This is a method that's based on something called projected augmented wave, which is another kind of pseudopotential. And push that to silicon. Now Z is increasing, right? So I need more memory, you need a higher cutoff. And now we're going to be working with calculations of 100,000 Rydbergs. It works. Actually, it's amazingly converging pretty fast. What you need, though, is you need a code that's capable of changing cutoff on the fly. You start with a small cutoff. Start with a 5,000 Rydberg cutoff, and then switch to 10,000 and 20,000 and so on. This is similar to what's known as the full approximation scheme in the multigrid methods, for those of you who might be familiar with that. We just keep increasing the resolution during the calculation. And you do that here by interpolating on finer grids as you go. You cannot do that with conventional codes because you would have to save the wave functions. There's no way you can save those wave functions on disk. You end up using something like 100 or 200 terabytes of memory, right? So this is a one-shot calculation where you just increase the cutoff all the way to 100,000 Rydberg and get your result. Right? So we claim to have computed the band gap of silicon within PBE, and that's a little bit underwhelming, right? Something we were doing 30 years ago. But this time we claim that we have done that without approximations at all, we claim, right? This is converging the all-electron problem to large plane wave cutoff. So that's our value. The pseudopotential from our collection is doing remarkably well. That's weird because we never really optimized it for excited states. It seems to work. It's another kind of mystery we'd like to understand better. Why does it work so well? VASP is doing pretty close as well. If you use Gaussian functions, it can be a little bit different. And I'm no expert in choosing Gaussian basis sets. And probably, I don't know if those choices are considered good enough, but they can lead to somewhat of a different result. But also, this allows us now to estimate this kind of cross-XC error that I mentioned before, right? If I use the scan functional with this PBE potential, the SG15 that we had developed, how far am I? Well, I can know that because now I can run this all-electron PW calculation with scan. All electrons treated with a scan functional and converge it. I get this gap. If I use the SG15 potential, I'm pretty close again. That's surprisingly good. I'm not even sure why, if I understand why. But I can verify this. And there have been some claims in the literature that for scan, you really need to develop a special pseudopotential scan. Well, the message for this case is not really. It seems to work already like this. And one last thing I want to show as in terms of sort of the validation of results using this all-electron plane wave calculation is a computation of forces. Now, I mentioned before that we're trying to do molecular dynamics in the end to sort of, simulate our properties. So it's important that the ionic forces are accurate. So one thing we are asking sometimes is, how good are the forces when we use pseudopotentials? How good are the forces when other people use maybe Gaussian basis sets? Who is right? Who is closer to the truth? So now we're able to answer that question. So what we did here is we took a snapshot of a 64-molecule liquid water simulation, something that we had published before, and that's something that was done with William Dawson back in 2018. That's a data set of simulations of water that can be used as a source of snapshots for representative configuration of water molecules. So now we can compute the ground state and the forces that result in a PB with a PB functional that using all-electron plane waves, and that requires 30,000 Rydberg. We claim that the forces we get are converged to this value because if we change the cutoff between 20,000 Rydberg to 30,000 Rydberg, it changes by less than that. And the conversion seems to be smooth. So what we do then is we take this value as our reference. We say that's the ground truth, and we compare other methods to that. And we see, for instance, that if we use our SG15 pseudopotential, the maximum force error is going to be 2 × 10⁻³ . But if we use the CP2K code with a triple zeta with polarization basis set, something I'm not familiar with, but that's used quite frequently, the error is a little bit larger here. So I have this distribution of errors, right? So the vertical line at 0 would be our reference with the all-electron plane wave. And if I use this pseudopotential, I have a slight error that's distributed with the black line. But if I use CP2K, I have a little bit broader distribution. So that's the first time we could actually assess the quality of these methods against a reference that we claim is the correct converged PBE answer. All right, so a lot of remains to be done. This is actually very new, very recent results that we can do all-electron plane waves. What I would like to mention here in this audience as further goals would be first to try to formulate the pseudopotential problem a little bit more precisely with the help of mathematicians and see maybe make progress in that and help us understand errors. We would necessarily have to also invent more elaborate cost functions to try to improve these pseudopotentials. Also, what we're interested in is for these high cutoff calculations, can we obtain bounds on errors, right? Obviously, on the energy would be nice, but also on the forces, the stress tensors, on the excited states, on other properties. And in that context, I'm very interested in the work of Eric and Geneviève Dusson, who were working on developing these post-processing methods to try to understand the error that we make when increasing the cutoff of a plane wave calculation. That's precisely the context we're in. We have a plane wave Kohn-Sham calculation, and we're increasing the cutoff. I would like to understand if we can bound the error that we're making on various properties. So I think that will be certainly a source of interesting discussions. Well, that's what I wanted to say about pseudopotentials and reference data. So generating reference data for me means pushing the plane wave method to the limit and generating data that's converged. Now, in the a few minutes that remain, I just want to make a few comments about another topic entirely, which is the question of hybrid DFT simulation and how we can accelerate them. And that's been kind of a recurring theme in this context here in these workshops. And it's something that refers to work that is not very recent, something you've done a few years ago, but I wanted to mention it to join the discussion of the generation of localized orbitals in many contexts. So here is just a slide that I want to just skip over pretty quickly, but just show the exchange energy here represented in terms of the Kohn-Sham orbitals here, for instance, and simply pointing out the fact that that's a very costly quantity and requires the evaluation of many of these exchange integrals. And that if you use Fourier transform properly, you can reduce that to an n cube log n cost, where n is the number of orbitals. It should also be pointed out that chemists have pushed that to a high level of sophistication for localized basis sets, pushing basically this whole method to be order n, or n log n. So in the context of extended systems and plane waves, we're still kind of behind in that sense. Now, one approach that's been typically used to reduce the cost of these calculations is to try to localize orbitals and then truncate them so that we can avoid computing all these exchange integrals. And so that led to the consideration of Wannier functions, and it's been known and been shown pretty rigorously that they can exist and they are exponentially localized if there's a gap in a spectrum. The practical approach to that is to try to minimize the spread of a wave function by computing this quantity, the expectation value here of the position operator. And that leads to Boy's orbitals for chemists, and the same thing called Wannier functions by physicists. It's been seen both as an optimization problem, minimizing this function here. We showed that you can also look at it as a simultaneous diagonalization problem, which is just a different way to obtain the same thing. And so these maximally localized Wannier functions look something like this. If you consider the C60 molecules as an example here, if you take your, say, some randomly chosen eigenfunction of the Hamiltonian, it would be extended over the entire system. But if you compute the Wannier function that minimizes the spread by making linear combinations of all the eigenstates, you can obtain functions that are pretty tightly localized. So that was the basis for the approach that would truncate then this function and say, I don't need to compute all these exchange integrals because some of them are going to be localized in completely different regions. Therefore, the exchange integral is going to be 0. I'm going to save some computing time. Now, the comment I want to make is that this is all very nice with C60. It's all very nice for water. It's all very nice for diamond, silicon. But when you start looking at more complicated systems, it's not that easy, right? Consider here this slab of silicon in contact with water. It's not even the hydrogen terminating the surface. It's a nearly metallic system. It's a complicated object. And it's a snapshot of an MD simulation, too. How are Wannier functions going to be localized in a system like this? Can I localize all of them nicely to something tightly localized? And the answer is not really. You can truncate them in a real space, but you don't really know what error you make when you truncate them. So the statement I want to make here is really this one. So the Wannier functions can have different localization properties in different systems. And to control the error when you start truncating these functions is actually very tricky. Right? And so what I wanted to sort of advertise here is a technique we use to address that problem, but sort of backwards. Instead of saying, I want to try to localize my wave functions as much as I can and then truncate them, I'm going to ask the question backwards. I'm going to say, what domain can I use in which an orbital can be localized for a given error when I truncate? Right? So basically what I'm saying, I'm going to say the 2 norm of my orbital cannot differ from 1 by more than a certain tolerance. Where can I localize my orbital? So here we basically take the approach where we define first the domain in which we're going to be localizing things. And we do that by just cutting our domain in all directions and then subcutting the subdomains and so on. And we find that actually also using a simultaneous approximate diagonalization, we can actually find these orbitals, which linear combinations of orbitals can localize best in these domains. So just to summarize the way it looks, this is what happens if you take, for instance, a carbon nanotube. Those are the localized orbitals that come out of such a calculation. So basically, they tell us how localized they can be within that tolerance. And some of them can only be localized here, for instance, in a quarter of the domain. This one in 1/8 of the domain. This one as well. This one, not at all. If you want to maintain this tolerance, you cannot localize that orbital. That's something that's just a property of this system. So we're not arbitrarily truncating things. We're setting a tolerance level and say, what can be localized? And the whole point is that usually most orbitals can be localized, but there are a few that cannot. Yes?
What tolerance for these pictures are you, I mean, is it like
1%.
6 or what?
No, 1%.
1%.
On the charge, right? If you tolerate a 1% leaking of the charge out of the domain. So this led us to look at very different systems, and in particular the ones that are of interest to us, and they involve a lot of surfaces and liquids and such. Just pure water here, I'm showing here how much of the volume here, fraction of the total volume, a localized orbital would occupy. So it's hard to see, but this is 0.08. And I'm just numbering my orbitals here. 512 of them. They're not all as well localized, but the most extended one would occupy something like 0.03 of the domain. That works perfectly well. That's why everybody does water when they talk about localizing orbitals. Very nice. If you now consider a system in which you have a bunch of tungsten oxide here represented by this slab in contact with water, well, it's a little bit worse, but you still have pretty good localization here. The most extended ones are still occupying a small fraction. This one is more tricky. This one is just silicon with water on top. Nearly metallic. Not a good situation. And there are states that you can't localize in this system. You see that now the scale is different. This is 1 here. Some functions are going to localize very well, mostly the ones in water, some less well. But then there's even 1. It's just going to be delocalized entirely. Nothing you can do about that one. And you don't want to truncate that one, because you're going to make an error, right? Last one is bulk molybdenum. That's kind of just the most extreme case. We say, well, that's a metal. What can you hope there, right? What can you hope in a metal? Well, turns out there are semi-core states that are these very tight d orbitals. And those can be localized really well. They stay on 1 atom. Okay, maybe that will give you some gain. All the other ones that are in the conduction band really cannot be localized at all. So this is what the method tells us. How localized can these orbitals be before I truncate them? And then I know what error I make. So we use that to accelerate Hartree-Fock calculations. And I see that I'm running out of time, so maybe let's just skip over that. It's just me saying we skip some exchange integrals that we know are going to be very small. One thing that we know also is that we make always a positive error, because all the exchange integrals have the same sign. So if I skip one, I know what kind of error I make. I know the sign. So I have, in some sense, a variational approach. And that gives us something where we have a method, and it's kind of in the spirit of this workshop, says, well, what are certified methods, right? I have a parameter here, which is my tolerance, that I can reduce all the way to 0. Here I pay the full price of the Hartree-Fock calculation. But if I let it be finite, the cost of my calculation decreases sharply, but the error grows. So I can play with that number and see where I have kind of a sweet spot, where I get less of a cost, but not too much of an error. But importantly, and that's in contrast with some methods that do truncation of Wannier functions, I can reduce that to 0. I can really see what the error is continuously all the way to 0. That allowed us, in particular, to do MD simulations, so we could reduce that cost of Hartree-Fock to the point where it was feasible to do molecular dynamic simulations where we compute the exchange at every time step, so that's pretty expensive. And we can start discussing differences between density functionals like PBE and PBE0, which is a hybrid functional for the properties of water. And that's a longer story that I cannot really embark here. So in summary, I tried to do 3 things here. First, describing pseudopotentials for an audience of mathematicians and showing you how messy this is. And maybe we can try to find ways of making that a little bit less messy. That would be the hope. They can be improved. We might define better optimization cost functions for that. They include more properties than we have now. The main point I wanted to do next is all electron plane wave calculations are possible. Yes, computers are getting big. It's a bet that they will get even bigger. But one day, I bet we will use that for reference calculations. It's just so simple. For that, we need a norm-conserving analytic regularized potential. I insist on the norm-conserving. It's a key idea here. We need a scalable code. That's quite critical too. And with that, we can provide reference data sets. So we can verify convergence. And finally, the last point I want to make was this last discussion on localizing wave functions, and there are different ways of doing that. So with that, I'll stop here, and thank you for your attention.